So this evening I'll be presenting on multispectral imagery on Google Earth Engine, right? So basically, what is a multispectral image? So we have quite a few orbiting platforms for the purposes of Earth observation. The European Space Agency, NASA, Russia, China, a few other countries have put multiple platforms into orbit for the purposes of Earth observation. So, for example, all of these are the satellite launched by the ESA in the past 10 years. And one type of Earth observation is using a multispectral imager. So what our eyes see the colors our eyes see can roughly be approximated by combining the colors red, green, and blue, right? What an MSI does is that it can pick out light frequencies outside of the visible range. So the bands visible here are from specifically the European Space Agency's Sentinel-2 platform. And it can view frequencies of light outside the visible spectrum. So if our visible spectrum of light are here, red, green, and blue, there are bands in the near infrared, shortwave infrared, and there are a few other satellites that can actually see into the thermal infrared range. So for the purposes of things like measuring the temperature of the Earth's surface or oceanic waters, some satellites also pull out the thermal radiation from the Earth's surface. So this specific satellite is called Sentinel-2, and it consists of two satellites in sun-synchronous orbits about the Earth, right? It was launched in 2015 and 2017, and the ESA posits that it would remain in operation for the next 7 years, so at least until 2023, 2024. The Sentinel-2 carries a multispectral imaging sensor, and this is actually the website. The images from Sentinel-2 are 10-meter resolution in the 13 spectral bands from the image shown before, and a 5-day revisit time. So 5-day revisit time means that these pair satellites would have a complete coverage of the Earth's surface between latitudes 84 north and 84 south every 5 days. And sun-synchronous means that it is able to take advantage of the most illuminated parts of the Earth and accommodate for things like shadows and reflections. So from multispectral imagery, because there's so many bands, right, we can't see outside of the red, green, and blue. We have to apply false colors to the various bands outside of our visual spectrum. So for example, this image here is a false color composite of something called the Urban Area Index. And for the photo scale, we can apply false colors to highlight green, which is vegetation. Anything with a reddish tinge is human-made. And because of the way this index works with water, water is black or blue. And like you can use this for stuff like flood mapping, where flooded areas typically is much darker than your surrounding land. And that's because water nearly completely absorbs light in the middle infrared range. This is just a shortwave infrared for central Trinidad, and very similar to the image above, water tends to absorb a lot of shortwave infrared and a lot of near infrared. So I took this specifically to show the areas of the Caribbean Swamp, where most of the shortwave infrared is absorbed at a very high level. So again, this is like used for flood mapping. This is a particularly useful index. So called the Normalized Difference Vegetation Index. It measures the state of plant health for a given region, right? Based on how plants tend to reflect particular frequencies, right? Chlorophyll strongly absorbs visible light, and healthy leaves tend to reflect near infrared. But as vegetation tends to degrade over time and the leaves become, for lack of a better term, spongy, the rate of reflection for near infrared tends to decrease. So you can actually take an image region and average the normalized difference vegetation index over time and calculate the quality of vegetation for a given image patch. Another commonly used index is the normalized difference water index. So this is used for things like coastal monitoring and to a lesser extent flood monitoring. So the most prominent use for this is to really gauge water stresses. So that has a lot of impacts on how crops tend to grow both on land and coastal regions. Because water absorbs shortwave infrared so much, the level of shortwave infrared in these multispectral images, it tends to be quite low. So if we inversely color the level of shortwave infrared in a particular image with blue in this case, we can accurately map water content around a particular area. So for example, this is the western tip of Tibet. And these are just a few other examples of what you can do with multispectral imagery. So this is, for example, just in the infrared band. So we're back to that water coast mapping. Normalized difference vegetation for central Canada. There's a whole list of indices that have been derived over time for different purposes. This is wildfire mapping, which has become particularly relevant over the past few months. Now, in order to generate these useful indices, you typically have to process multispectral imagery to a greater extent than you would process a typical 3-channel image or a typical camera image. So you have to take the ESA calls the various processing levels. So level 0 is your raw binary data. Consolidated level 0 is when you separate all the binary data into different bands. And there's level 1 and level 2 data. However, this entire process is typically very computationally intensive. And for example, if I want to observe a particular patch of land, and well, for a given period of time, I have to hope that the satellite was passing over at that particular point in time to get what I'm trying to observe. Else I'd have to stitch together 2 adjacent satellite images and then do that for specific points in time in order to, for example, generate a time series. And this step especially, apologies for lack of a better resolution, this was the diagram made available by the ESA. But I think the point that they're trying to bring across is made kind of clear when you go from the kind of hazy level 1A data to level 1B and level 1C data. To move from level 1A to level 1B and 1C, you have to perform radiometric correction. So that has to do with accounting for the curvature of the Earth's surface. For example, in this image, this is before radiometric correction and orthorectification. The mountains look kind of weird, right? If you look on the image on the right, the image looks a little more natural as a top-down image. And that's because, for example, if you picture a pin on a page, right? Ideally, what you'd want to observe satellite imagery by is directly top-down on top of that pin. So all you should be seeing is probably a circle. Because the satellite is not able to view the Earth's surface at exactly 90 degrees, and because this curvature is not uniform for latitudes, so around the equator is more curved than near the poles, you have to perform orthorectification and radiometric correction on all of these images to even begin to start using them. And this is just an image showing how that's typically done. And for example, if you want to observe a very large patch on the Earth's surface, you'd have to perform orthorectification in something such as the Sentinel Toolbox or NASA's Earth Engine Explorer, and piece these together over time. So it's a very involved data cleaning process. This is just a closer look at the 2 images from before. So again, the appearance of the mountains here tend to be truer from a top-down perspective, which is what you want. You want a satellite image that looks as though it's taken directly from the top of whatever you're observing. Else you'd have to account for the curvature of the Earth and the weird shadows and the perspective distortion at every point in this image, or at least within some some segments of this image. Sentinel-2 also provides a second level of processing called level 2 data. So it's essentially an image segmentation mask where they apply, well, a rough segmentation algorithm to break the satellite imagery into different classes. So for example, water, land, different types of land, cloud masking, etc. Now, in order to actually access all this imagery, like I mentioned before, you can either use something like the Sentinel Toolbox or NASA's Earth Engine Explorer. And the process is find an area that you want to observe, hope that there's a complete image for that region. If there isn't, you have to find a bunch of images that happen to overlap your particular region and stitch them together, perform auto-rectification or radiometric correction. And then, for example, let's say you want to do a time series for that particular region, you'd have to do that for various points in time and collate them somehow in a custom script, right? Whether it be whatever image processing scripts it's using. So in addition to all of those methods, you can access satellite imagery via Google Earth Engine. So Google Earth Engine is a catalog of satellite imagery and geospatial datasets with planetary scale analysis. It's built upon Google Cloud Platform, and it has a wide variety of datasets. It has been around since about 2001, but it's only when the Landsat set of imagery was made publicly available in around 2007, 2008 that it really began to gain some traction. And within the past 5 or 6 years, there have been quite a few new satellites being launched and being planned to launch using the European Space Agency and NASA plans to launch, right? So Earth Engine is available via JavaScript, Python, and via the REST API. However, the REST API is typically a very niche use case, as if you want to really export large amounts of geospatial data from Earth Engine. So if you want to visualize or generate charts, the way to go is typically the Earth Engine code editor, which is a JavaScript interface, which I'll go into a bit later, or via Python. So you can actually use Earth Engine via Colab or a Jupyter Notebook or some offline IDE. Now, within Earth Engine, you have available quite a few features. You can your typical computer vision algorithms are built into the code editor, so you can do things like convolution, apply your convolutional filters, your Sobel filters. You can perform wavelet transforms directly in the code editor. Recently, they also introduced the usage of TensorFlow models in the cloud. However, you have to upload your Earth Engine steps into GCP compute cluster and then bring it back into Earth Engine via the Earth Engine console. A host of other image processing features also available, like canny edge detection, corner detection, etc. And this is just a general overview of the code editor, but I'll get into this a bit later. So let's say you want to access the Sentinel-2 data, which I went through in before. You typically want to select a data set, apply some sort of filtering, whether it be by region or time, apply some sort of post-processing, and then visualize it. So as opposed to the process of selecting images for a patch on the Earth's surface and manually aligning them and selecting them, searching for these images at particular points in time, what you can instead do using Earth Engine is load an image collection. So Earth Engine will search for images that are part of the particular image collection it is searching for. So whether it be the Sentinel-2 satellite that I showed before, or Landsat imagery or Modus imagery, you can actually select it using image collection, filter by date and bounds. So this is the part that greatly eases the processing of geospatial data. And some satellites require quality filter removal because clouds are water vapor, and the interaction between your multispectral imaging bands with water vapor is sometimes not, it can't see directly through the cloud in certain instances. You'd want to filter imagery such that the amount of pixels in that particular image, to, at least 20%, at most 20% is cloud. Now, math is very simple in Earth Engine. For example, the indices that I was going through before, if I wanted to construct some sort of index, I knew it consisted of a series of subtraction, addition, or exponentiation, etc. All I have to do is select the particular band I want to select from my images, right? So the near infrared here, in this case, the red, and call dot subtract. The alternative to this is, again, selecting the images by hand and aligning them and then doing the manual subtraction and then having to do this over time. In this case, you can do subtraction for an entire time series in one go. The same thing for adding pixels and exponentiation. Another advantage of doing it like this is that you can also accommodate for very complex expressions or complex image math. So for example, if I wanted to calculate the enhanced vegetation index, all I have to do is select the particular bands corresponding to, in this case, near infrared, red and blue, and use a string to define what sort of math operations I wanted to do with these images. And again, this can be done to a set of images over time or over a large area on the data sets. For the enhanced vegetation index specifically, another useful, and this is not just limited to Earth Engine, but another useful operation is spectral mixing. So this is where you assign particular frequencies of your images to different categories of cover. So for example, urban cover versus vegetation versus water, you specify your spectral end members, which just define what these different things are represented by in the multiple bands that are returned by the Sentinel-2, and you call dot on mix on your set of images. So what this does is that it assigns urban cover, vegetation, and water to red, green, and blue. So to just give you an idea of what that looks like is if I spectrally unmixed, this is the western tip of Tobago. This gives a rough segmentation of water. So water was blue, vegetation was green. So vegetation is more or less covered, and then urban or human-made structures are red. I purposefully didn't tune this image because the point of spectral unmixing is to segment a particular region. And depending on the composition of the land and what type of buildings are present, etc., a lot of these methods need tuning depending on the region that they are focused upon. So this is just a more specific example where I'm loading the Copernicus Sentinel-2 multispectral images, filtering for 2016 and filtering around a particular point. Another powerful thing in Earth Engine is using reducers. So for example, if I loaded this collection in and called reduce using a minimax reducer, it would return two sets of collections, one with all the minimum points and one with all the maximum points. And sometimes we want to difference both of those to generate other useful metrics. The concept of reducer generalizes further than that. So I can reduce between bands, I can reduce for particular regions, I can generate statistics for a given region, or it can even pass a kernel, so a convolutional kernel over a particular image using a reducer. Another type of reduction is using histograms. So, for example, in this image, you can generate a histogram for this particular image and view the separation of the various bands, and then apply false color to separate out coastline from shore. And a particularly useful application of this is monitoring the erosion that the coastline goes through after time. So as you see more water, or the spread of water becomes wider and land goes down, you can kind of quantify how much coastal erosion is going on there. Also, you can reduce for a given area. So in this case, I drew a bounding box around South America. This is directly from the Pigeon Console, and did a normalized difference vegetation index over time. So this can be used for like forest mapping and monitoring for various agricultural applications. Now, this is the normalized bloom ratio, and I decided to do this particular demo because in the past few months, quite a few places have experienced catastrophic wildfires of magnitudes we're not really accustomed to. So California, Greece, Turkey, etc., Australia in 2018 have experienced quite a few wildfires. Now, the normalized bloom ratio was proposed in the 1990s by two independent researchers, and it basically highlights burn areas in large fire zones by combining near-infrared and shortwave infrared. So near-infrared is reflected heavily by vegetation, so that's why we use it in the normalized difference vegetation index. However, burn areas tend to reflect shortwave infrared quite a bit more than vegetation does. So we can kind of find the difference between your shortwave infrared and your near-infrared, and then normalize it by its sum and come up with something called the normalized burn ratio. So to take this one step further, we can take the normalized burn ratio before the fire and then before the fire and then after the wildfire, and map how much area has been burned. And you can do this over time to see the creep of fire of burnt area over time. So this is the Earth Engine editor. Just confirming you're seeing the Earth Engine editor and not this slide.
We're seeing yeah. Mm-hmm.
Okay, cool. Right, so this is the Earth Engine editor, and it's a JavaScript editor built on top of the Google platform. So for the normalized burn ratio, right, the first thing you have to do in using Sentinel-2 data is map out the clouds, because as I said before, clouds typically interact at multiple wavelengths. So the way you do that, and for specifically Sentinel-2 images, is by selecting the quality band and selecting, well, there's a cloud band and a cirrus band. So you want to select images or mask out images, or mask out the portions of images that don't register as cloud or cirrus. So for example, you might see particular white patches where the image just looks kind of blank, and that's because we've masked out any clouds or cirrus from those images. So, and these are the same steps that I went through before. Select Sentinel-2 imagery for a period of time before the fire. So this was last year, April. Filter for clouds. So again, filtering such that the percentage pixels in a particular image, less than 20% of it is cloud. Mask it using the function above, so to remove again the cloudy pixels, and then this function clips to a particular region. So I can draw a polygon here and say that, okay, I only want this image collection for this particular region. And I can do that for dates after wildfires have occurred. This is for the purposes of just displaying the true color image, so the RGB. And as I went through before, we have to apply some sort of false color to multispectral imagery. So we define NBR visualization. So this is just a range of values for which we want to map a palette of colors to. So 0.5 happens to be black, or near black, and 1.3 happens to be bright white, and it's a spectrum of color ranging from very dark yellow to very, very bright yellow to white. So the same math functions that I went through before, using subtract, using divide, etc. Again, the alternative to this would be taking images for various periods of time and hoping that they overlap, if not stitching them together, and then computing these indices by hand almost. So select the near infrared, shortwave infrared, and construct my index, so the normalized Boolean ratio before and the normalized Boolean ratio after, and find the difference. So that's what we see here. So if I turn off, and this is directly in the editor, if I turn off the bounding box I drew and turn off the normalized Boolean ratio, we can actually see where the earth is a bit scarred from wildfire. So if I turn on the normalized Boolean ratio, we can actually map what has burned thus far. And so you see these gaps here. Right, so you're seeing these gaps here, and that's where Earth Engine has masked all the cloud, right? But using the palette that we defined, we can kind of visualize how far fire has burnt. And for example, this is at the southern coast of Turkey for last week, and you can actually see the fire front here. Another interesting demo, and I only kind of went through this today, was for the purposes of actually mapping the fire front. So in Greece, we had a few huge wildfires last week, and fires tend to be very bright in the shortwave infrared spectrum. So that would be, that would be band B12 on Sentinel-2. So this is for the period from the 3rd of August to the 9th of August, and I just took a mean across those dates and visualized band B12, right? And all these functions are available in Python, so you can actually use almost the exact syntax, apart from like the very specific things between JavaScript and Python, a colon for functions instead of brackets, etc., to do these sorts of visualizations. So this one in particular visualizes the fire front in Greece over the past week. And if I did the same thing for normalized Boolean ratio, it would actually show all these areas that were burned. I'm going to just turn off the fire front so you can see exactly where the fires have reached, and using particular bands from the multispectral imager, you can visualize where exactly is on fire. I won't actually run this particular demo because I don't want to risk doing that while I have a Zoom call running. So this is just a demo that shows that you can also do it in the Colab environment. So it's a bit less interactive, where you can really turn off and on the layers in the same way as I was doing before. But the function calls, etc., are pretty much the same. So you can do the same land cover mapping, fire doing front mapping, with the advantage that you also have all the Python libraries for typical image processing at your disposal. Okay, and that takes me to the end of this short presentation / tutorial. If you'll have any questions, feel free to ask.
Thanks, Aadidev. Nice presentation. Actually, I'm glad you talked about that fire stuff, because we actually have a project with Earthmedic on fire stuff. So maybe I'll chat with you about that offline. But thanks, interesting stuff.
That's rough. Any other questions?
Yeah, Dev. Was this the project you were mentioning that you were using Rapids for?
No, actually, this wasn't actually part of that project. It was the engine I was using for that project, but I was using a different set of satellite data actually.
Okay.
Yeah,
but
I was using an engine.
Okay, but could you apply Rapids to this, like to speed up computation, or would it be too difficult?
No, yeah, you definitely can.
Okay.
Yeah, via the Python APIs you can.
Okay, cool. All right. Well, that machine is unfortunately down, but I guess when it goes back up, you could try.
Yikes.
Yeah.
Right.
Nice presentation, Aadidev. Just a question: how would the Rapids environment be applied from Python?
So you can export or download Google Earth imagery into Python, and then you can export pixel values, so actual pixel values as time series data or in some other rectangular format. So probably indexing by latitude and longitude and a given value for each band. And that could be taken in as a data frame directly into Rapids because it'll be purely numerical data.
Oh, okay, cool. I understand. I thought you meant Earth Engine API could interface with Rapids, but I understand now. You could just download the raster or a feature collection, and okay, cool. I understand.
Yeah. And it lends itself particularly nicely to that because the kind of output you get from that are very tall, thin data frames, which is exactly what Rapids kind of is, where Rapids is very useful for.
Yeah, there's a library called X-Array Spatial that may be of interest to you.
X-Array Spatial.
Yeah.
Yeah,
especially for especially if you have the geotiffs or the any form of rasters in general. I think Torin knows the guy that wrote X-Array Spatial as well at MakePath.
Okay, cool.
Just a comment, right? It's like, don't you find it amazing that the European Space Agency makes all of this stuff for free? Like it's hard to imagine it sometimes. Yeah, such a wonderful resource.
Yeah, agreed. And like all this is open access. Even some of the tools are open access. And it's like, here's all this data, and I think it's better like for humanity as a whole with all this data available. We can take advantage of it much more than if it were locked down.
Yeah.
So it's a really cool thing. It's kind of unbelievable, but it's really cool.
Have you played around with the software called Snap?
Yeah, actually.
Okay, right, nice.
So that was actually what I was comparing Earth Engine directly to, because I was trying to do the same things as in Earth Engine, doing time series over time, and I was like, this is a lot more data intensive, a lot more pre-processing intensive than Earth Engine, how easily Earth Engine allowed me to do it.
So, sure. You thank your lucky stars that somebody did the pre-processing and then they put it on the Earth Engine catalog rather than you having to go and do all of that yourself.
Yeah, agreed, definitely agreed.
Yeah. So have you done any of the NASA tutorials? NASA has a whole list of courses, throughout the year. Yeah.
Yeah, the webinars have been like really helpful, and it's usually like really long, but it's really in depth, the kind of things that they go into. So yeah, I was checking out some of the webinars, the ASDC webinars too.
Yeah.
Really cool
they have one on Small Island. Yeah, coming up soon. Yeah.
Oh, that's the one in September, is it? I think I registered for that.
It should be in a few days. It should start on the 13th or the 14th, I think. Yeah.
Okay, I'll look into that one.
Cool.
Thanks.